So it's a great honor for me to introduce Professor Michael Hogele from University of Los Andes. And Professor Hogele is graduated from Humboldt University, and he held postdoc positions in Potsdam. And nowadays he's an associate professor at Universidad de Los Andes. He's a leading expert in Levy processes, and he works on the interface between probability theory, dynamical systems, and mathematical physics, and differential geometry. So he's really one of the leading experts dealing with Levy process, and especially with geometry and SPDEs. So it's a great pleasure for us to have you here. Thank you, Michael.
Thank you very much. Well, leading expert. I'm going to tell you something about some recent work. First of all, let me thank you very much for the kind invitation. It's a great pleasure to be here, and also an honor. So I'm going to talk about some recent work I've been doing with two of my co-authors. So one of my co-authors is Luisa Estrada. She is a former pregrado student from Los Andes. She's now doing her master's in Warwick. And Alexander Steinecke, he's working in Austria at the Montan-Universität Leoben. I'm going to talk about deviation frequencies and their application to Brownian path property approximations. So first of all, I will spend quite some time, so the first three items of the talk, about what are these kind of deviation frequencies. And I will show you that these are simple elementary extensions and quantifications of the Borel Cantelli lemma, of the first Borel Cantelli lemma. Okay, I will make a short repetition for those who are not familiar with this, and then we will see that there are many, many applications which are quite natural to see. First of all, we start with the most elementary things. So we have a probability space, and we have a sequence of events, and then of course we know that the limit superior is just the set of all omegas which are in infinitely many of the ENs. Okay, so if you make the painting of the intersections, so you have omega here. So for omega, here we have E1, here, okay, so this is E1, E2, E3, and then of course you look in how many of them are here in nobody, here none of them, here are in 1, here in 2 of them, and here in year 3. And of course, so the lim sup are just all those omegas where we are in infinitely high towers of intersections. So one natural notion to study this is of course just counting in how many you are. This is the overlap statistics. And this means the lim sup is just those omegas which have an infinite overlap. Okay, so it's just repeating once again the same. Now the classical Borel Cantelli lemma just tells you that if you have a probability space, you have these kind of events, and the probabilities go to 0 sufficiently fast in order to be summable. And once this is the case, then you have that the lim sup is 0. Okay, this means that the height of the towers, if you pick at random one omega, the height is finite. Okay, so one natural question is of course how high is it? And of course this is one of the main questions here. So if O is infinity with probability 0, this means, okay, this is just the definition. So there are two proofs. One is the classical proof. So you pick some omega, you take the definition of the lim sup, and you estimate the intersection of all of them by the intersection of only n of them. And you can see that this is nothing because you have here something which is decreasing. You can just estimate it by the probability of the union from n to infinity. So a union and bound argument, just estimating the union by the sum, which should be finite by hypothesis. You see that if we have a series and we look at the remainder of the series, of course, this tends to 0. Okay, this is just the classical thing. This is how far what is classical in the textbooks. But we only see that O is finite almost surely. There's nothing about the mean, for example. Okay, but you can, of course, prove it much easier, and you can already say something about the mean, because what is the mean? Yeah, okay. If you can justify that you have this kind of limit and you can pull it out, you can see that O is just the sum of the indicators, and if you can just switch the sum and the indicators, you can see that this is just what you have finite. All right? So you say you know much more. You don't know only that it's finite almost surely, but that the mean is finite. Okay, this is of course a much finer information. And so what you need is this kind of summability. And there's a lot of information already there which we know from the historical development, let's say. The law of the O is very well known. Of course, there's some kind of inclusion-exclusion formula, and you can say this is just the sum over all k intersections of the sets you have. Of course, such kind of probabilities and even summing of them is not at hand. So this is something in applications which you don't have. Nevertheless, the only thing in order to have something like O finite is that this is going to zero fast enough. But typically in applications, it's not only merely being summable, excuse me, but it's going to zero much faster. Typically it goes to zero, for example, at an exponential rate or something which is very good. So these are the ENs. Okay, pardon, the E is the same. These are the same. This is the EN. Sorry, this is a typo. Yes, these are these. Oh, in order to have a finite O, you only need that the probabilities go to zero fast enough. Okay, but you have much better. In general, you have much better rate, and you can exploit this. So you should be able to translate this excess of summability in something like higher moments, higher summabilities of O. Okay, so this is quite natural to ask. And here, higher moments are maybe the thing to go. Of course, I'm not the first person to look about the first Borel Cantelli lemma. There are a lot of things to be seen. So, in general, there are two lines of research. Just, time does not permit to go into these. Just two lines. The first thing is, there are many extensions of the summability condition to have O finite or finite on some positive set of positive probability. So this is the first line, and there are a lot of results there, also conditional results, etc. And then the second part is about the second Borel Cantelli lemma, which just talks about divergence. Okay, so how fast things diverge if you have non-summability for independent events. So there's a lot which was done, and I will just restrict myself to the questions of this kind. So if we only have the probability of the ENs tending to zero at a certain rate, what can we say about higher moments of O? And how does this change and can be improved, hopefully, if we have the monotonicity, so they are nested, or if they are independent? Okay, what can we say? And then we would like to apply this in a very natural setting. And where do we apply Borel Cantelli? Typically, it's the strong law of large numbers. You have the weak law, and then you just strengthen it by controlling the rate of convergence of the error probabilities. Okay, this is one of the paths we want to go. So, okay, here are some things which have been done before. For example, there have been results about martingale differences by Friedman and also in the Williams. Then we saw some very recent results where a certain decay, the tail of the summable probabilities appears. And there are applications of the Schütte-Nesbit formula which have been recently in information theory, just to see that the literature is correct and it's complete what has been done there. So, the good news is we start with the nested case. So we have that the next event is always included in the previous one. We have some kind of weights, and we define just some kind of the sum of the sequence, and this is just, so to say, the discrete antiderivative. And the good thing is that we can write down the moments of order S just in terms of the sum, of the weighted sum of the probabilities. So, remember, before we wanted to have, before we only had the summability, now we can introduce some weight. And what we gain in case of having ENs, which are nested, that we have a very precise, a precise formula for higher moments. Okay, what kind of ANs can there be? For example, if we need only summability, for example, that the P is something exponential, we can also counterweight it in order to still have something summable with another exponential, which is maybe of a lower exponent. All right, and so if you sum exponentials, you get a geometric sum, which is still exponential. Okay, you can just write it down. Okay, we'll see examples. So the proof is very simple. You start with some fixed depth, and then you use some summation by parts. It's really straightforward, nothing very deep. So here you can see the formula. You have the PNs, which are just our Fs, the ANs, which are just our weights. The good thing is that if we have something nested, that being exactly in K of them is just being in the K and not being in the K minus first one. So this is, we have a very precise control of the probabilities. So this is what appears here naturally. So just if you rewrite it here, everything's just plugged in here. And what we obtain here in the GNs is just the sum over the ANs, and the sum over the ANs is just our this antiderivative which we have here. So if we do this, we obtain here our formula. We can simplify it a bit. And what we get here is just the moment we were looking for minus the same term which appears here on the left and the right. So we can cancel this term, and then we can just pass to the limit by monotone convergence. All right, so we can just let it grow, and the limit goes through. So once again, what do we have? If we have nested events, we can just counterweight the probabilities. And what we get are higher moments, which are just of order, just the antiderivative of the ANs. This is, okay, after some trying, this is quite really elementary. And now you can use it in a general case. In a general case, of course, you don't have weighted, don't have nested events, but you can produce them. Okay, what you do, you take the union from n to infinity, and then you have one, and what you lose is just one order. So you have the same setting, only that our events are not nested anymore. We have the weights, our antiderivative, and then we can bound these moments of order S if this quantity is finite. Look, before we had just the probabilities themselves here, and now it's changed by something which still is measuring the tail of the probabilities. It's just the sum of them, and it's the sum from n to infinity of these probabilities. So we're going to the antiderivative. Okay, we're just integrating or summing from m to infinity, which is also a measure just to to measure the rate of convergence. All right? Right, the proof is also very easy. This is it, nothing more. So our ENs are included in the union here, and these are once again nested. So the ONs are less or equal than the O tildes. Everything is positive, so these functions are monotone. You can estimate it by the expectation of S of O tilde. Here we have the probability of S of this is our previous result. And here we have just a union bound. So we estimate the probability of this guy by the sum of them. Okay, so it's disappointingly simple, but it's useful. Right, examples. If we have ENs, which are of some polynomial decay, C divided by n to the Q, then we have a relation between the moments we can permit ourselves. Okay, so we have P plus 1 less than Q minus 1. Here we are. And there we can estimate it by some zeta function. So this is finite. So what we get here are moments of some polynomial order. So if we have some polynomial decay, we have polynomials, polynomial moments, right? So this is a case which, of course, occurs very, very much. Then the second case is even, especially if you study, for example, Brownian motion or approximations of Brownian motion, because there are a lot of Gaussians, of course, appearing, and you have exponential convergence. So if you have some kind of geometric behavior or exponential behavior, you even have exponential moments. Okay? What you do is you just take 1 plus, and then you have, remember the sum. These are our ANs, and here we have the tail over the probabilities. You can just calculate or estimate them with the formula here. You can calculate, and you come to something which is finite. The special form here is interesting because later, if you use, for example, the Markov inequality, in order to bound the tails, you can optimize over these kind of things if you have all kinds of p's. Okay, you can still optimize over the p's and the probabilities. Well, now, what happens in a case? So we had the monotone case, we have the general case, and what about the independent case? In an independent case, of course, you have Kolmogorow's 3-series theorem, which tells you that essentially O being finite is equivalent of having, for example, second moments being finite, and this is equivalent, as it's calculated here, of just the sum being finite. Okay, this is a special thing. This means, in the case of independent moments, you already have second moments. But of course, you should have much more, and you do have much more. For example, this is the result by Friedman. By Friedman, you have that if you have in our typical setting independent events and you have our sum. So just to acquaint you with the notation, this is C1 because I'm starting in 1 here. So later on, we'll start later. So, okay, just to. So what we get here is an exponential, an estimate on the exponential moment. In fact, for all exponential moments. So if you have independent events, then you know that the overlap statistics has exponential moments, all exponential moments, and what appears up there is just the sum. Remember, this is just the sum. This means it's only the value and not the rate. Okay, so if you teach a series, okay, you have to acquaint the students that there's a difference between the rate of convergence and the value. Okay, you plus 1 gives you a greater value, but the rate does not change. Okay, so, and this is the same here. Here we have just the rate, and of course, for the purposes Friedman did in his article, it was way more than enough, but you want to do something better. So now, what can you use? What can you do if you have any kind of exponential moment? You use Markov's inequality here. Here you can see the moment, and then you have the probability of appearing here, and then you can optimize over those. And what you get here is something nice. It's e to the minus k log k. This is 1 over k to the k. This is already quite strong. This is because you have all exponential moments, right? You can optimize over them. Well, the proof is elementary. I don't go into this. This is just very, very elementary. Okay? Please? It's not that elementary. Okay. Then I'll make it. Pardon. Then I'll make it. Sorry. Sure. Where I define it? Here, this one?
So it's an expectation of the second line from bottom to top. This is the general case, the previous one.
The monotone case.
Monotone case.
Mm-hmm.
So how far is the second line from bottom to top? This expectation is not the definition of expectation of S of O.
Yes, but okay. Yes, you're right. Of course, this is the very, very beginning. But nevertheless, well, the definition is not about. Well, the definition of this would be that O has some kind of value, and not the ENs. So on the right-hand side is something different than just exactly. Okay, it's not this. Well, in case of S being just the identity, you're straight. You're right. This is the definition. You only have to justify monotone convergence. The only thing. But here it's not the same. So here you have to really go through the summation by parts. Okay? No. Once I'm going to fall here. All right. So what we get here is something which is quite nice. We can optimize here the proof. Okay. So what can we have here? We have R times here the sum. So these are independent, so you can plug it out. And now what we use here, we can estimate here by Bernoulli's inequality, and we get some exponential here. Oh no, what do we hear? This is so here we have the expectation of the let me see. E to the R, the okay, and you can, if you look at the case distinction, we have 0 or 1. you can really write it down as this kind of expression. And this expression is actually nice because you can just lift it to the exponent. This is x of the logarithm of this. And there we have something, logarithm of 1 plus something. Okay, and here you can estimate it by the exponential. You have a logarithm, and inside you have an exponential estimate. And what we get here is, as you can see, here we have some linear expectation, so linear estimate, logarithm of 1 plus something. Here we just estimate it by the sum. And what we get here naturally is the sum over the, so we can just pull back the sum. So here is no dependence on the ends here. So we have e to the r1, this is an elementary estimate, and what we get here is the sum over the probabilities. So this is what naturally appears in the thing. Okay, you can just go through it line by line. It's really a really elementary calculation. But the point is, you get here C1. This is what turns out, and C1 is just the value of the probability. So what you want is to include the rate. So first of all, this has a nice implication for the second Borel Cantelli lemma. Second Borel Cantelli lemma just tells us that if we have independent events, then we know that the non-summability implies that O is infinity almost surely. So you have infinite overlap with probability 1. But the counterpart, if it's finite, then we have already exponential moments of all order, right? And we can just write it down here. Now, we can improve this. If we just use another formula, we can estimate it differently. And the price to pay for this is, well, this, first of all, this is looks like a 1 over 1 minus something. This is some kind of geometric sum, and it is. And the only thing is, if you have geometric sums, is that the things whose power you're summing is smaller than 1. Okay, so this is what happens here. So we need some kind of condition that that C1 times e to the r is smaller than 1, and this is what we have here. But this is something which we're going to relax if we start instead of 1 in some kind of m later. All right, so we can just derive another formula, and this formula is quite nice. It uses the original distribution of O, which is known. So this is the Schütte-Nesbit formula. You can really write it down. So here we have the probabilities, and there's a well-known formula for the moments. And if you do this, you can write it down here. You can parameterize it. How does it look like? And you can see that it essentially looks like the sum to the power of n, where here several terms are just missing. Okay, you parameterize what this means, and then you can see that you don't have all of them. And if you estimate it by all of them, you have the sum to the n, and this is the thing we already know. This is C1 to the n. Well, and then we can just use our formula. Here we have it. We have our counterparts, which are just a case here. We just rewrite it, so we can just, if you look at only n events, then we only have at maximum n intersections. And then, okay, we can use our formulas. We can estimate this minus 1 can be thrown away. And then we can see that what we have here is just estimated by C1 to the n. And here we have our geometric formula. All right? So it really turns out it's just our geometric formula where we use the original Schütte-Nesbit formula. It's quite straightforward. And then we have just to pass n to infinity. Okay, so using this original formula, we get something which is at the first sight not so spectacular than it will turn out. What we get is that we can estimate the exponential moments by something where we look at CMs, as I promised you. The CMs are just the tail of the series, and this was, of course, the thing we were looking for since the very beginning. And we now take, for example, the CMs. We just took a look at the inverse. What is the M such that CM is smaller than the guy we had here? Okay, so we just start later. Okay, so we don't. This is a special case that the sum is smaller than this. Of course, this will not happen for any r. But if you fix an r, then you can just take the inverse, and then we get some kind of m where this actually happens. So from all m's on, you have this kind of formula, and then you can optimize it and you get this kind of formula. It still looks, okay, can you see, well, the first sight it's not so spectacular than what it is. We should look at examples. If we have our original case, we have independent, it's c times 1 over n to the minus p greater than 1. We take the delta, which appears also here, to be 2, and we can just plug it in, and what we get here is some kind of formula. We use Markov's inequality and optimize, okay? So this is Markov's inequality. We have 2 times, here we have the exponent which we have here, and here have 2 to the minus kr. Optimizing, we get something, once again, of this order. This is k to the minus pk. So it's already quite good. All right, so but this is something which we already suspected by the original Friedman formula. So this is not better, actually, than the Friedman. Now, if we go over to, for example, not yet, to the exponential decay, there we can do the same thing. Here we have some r squared. Looks suspicious. We have r squared, and we can make the same thing. We have the optimization. And what turns out is something of Gaussian order. This is e to the minus constant k squared. So we have a decay which is actually much nicer. And if we have even, because we will need it, something like a Gaussian decay, then we can see that we have even to the e to the minus k cubed. Okay, so you already, okay, you suspect how it should go on. It's not so strange to suspect, and you can also actually make sense out of it. Okay, so the independent part behaves very well. You can see you have even, if it's non-summable, it's infinity, always infinity almost surely. If it's summable, automatically it has very, very good moments, and we can even say in terms of the probabilities how good they are. They should be quite good, okay? Please. You should be able to. Yes, it should be able to. Should be adapted. Yeah, you can. I guess so. Yeah. So, okay. The idea, of course, is the strong law of large numbers, where you would like to apply this. Okay. So convergence probability just means that the error probabilities tend to 0. Okay. Just a fun fact by side. Well, of course, this is metrizable by the Q-fun metric. So this is, well, not a fun fact. It's very well known. We have the weak law of large numbers, which I just won't repeat here. And we have the convergence almost surely, just to have everybody on board. So, in 1999, Jukic and others just introduced the notion of complete convergence. This means just that the error probabilities are summable, and this implies, of course, the convergence of the random variables almost surely. All right, so the interesting thing is they never really exploited that one could use the overspill of the excess of summability in order to quantify this almost sure convergence additionally. Okay, this is what we are going to do. First of all, if you have convergence in probability, then of course you can always select subsequences which are again summable. So this is very, very well known. But one of the consequences of this is that almost sure convergence is not topologizable. There's no topology behind. Okay, what is the reason? First of all, by this memento mori example, so you have Bernoulli's 1 over n. The probability that of the omegas where they converge to 0 is 0. Okay, this means it's barely not summable, but the probability to go to 0 is 0. However, if you have just something which is a bit better summable, then it goes to 0 to 1, and you have already this exponential moment of the overlap statistics. Okay? So this means these are examples where we have convergence in probability, but not almost surely. This means the convergence almost surely must have, if there's a topology, a finite topology. So then you can take a sequence which converges in probability, but not almost surely. So some kind of exceptional sequence. But we know if something is converging in probability, then you can take a subsequence which again converges almost surely, because it's once again summable. And this is the contradiction. So the there is no topology which gives a topology, some kind of topology of almost sure convergence. All right, and this is, I guess, among others, one of the reasons why it was a little bit dismissed as a quantity, because mathematically it does not look sound. Okay, nevertheless, if you look at the law of large numbers, how is it proved? You just to do the same as always, you take a subsequence, you look at the law of large numbers, a subsequence where you have summability. So we have the almost sure convergence of the subsequences, and then you control what happens between the subsequences, right? Almost surely by the construction. So what we can do now is just to take into account the integrability, the moments of the overlap statistic. So what we do is we call something almost sure convergence with mean deviation frequency of order lambda if for any epsilon there is a function, just some kind of weight, this S for if you want so, such that for each epsilon we have some kind of finite moment where the O epsilon was just the overlap, the counting of how many times you will just trespass the difference of order epsilon before you finally comply, because it converges almost surely. This means this number will be finite. The question is, how many times will it happen? So how big is the probability to make more than k errors for some fixed level of epsilon? All right. And here we have several sufficient conditions. For example, yeah, if you have this kind of moment, so this is, remember, these are just the same notions which we have there. These are the tail of the probabilities. You have the weights, the same here, and the same is for the exponential case as we have here. So the result is this one. So far, if you have the strong law of large numbers, if you have second moments, and you have pairwise independent centered random variables, then you have convergence to zero or almost surely. But so far you could not take into account, or could not take advantage of higher moments, which typically are there. There are very few random variables which have only second moments and nothing more. So typically you would like to quantify it. And what we can do is we can say it converges to zero almost surely. And if you have moments of order 2q, then we take p being smaller than q minus 1, half of the moments minus 1. And we know that these kinds of overlap statistic has the moment p. All right, so this is what we can say. And of course, by this, we can say that the number of errors of level epsilon decays like k to the minus p for any of the p. And then, of course, you still can optimize if you want, etc. Okay? So this was one of the first results which we have here with Luisa last year. And of course, sometimes you have much more. You have an LDP, and then you should have something even better. And of course, you have something better. Of course, so this is written down in a. So LDPs are typically written down much more precisely, and you have the upper bounds and the closed, etc. If you assume that you have this kind of upper bound, so this means, and for any kind of A which is given here, then for each of the overlaps, so here we have the overlap is just in how many of the En of A's you are there, then you can estimate the exponential overlap, so the exponential moments of the overlap. And you can go to the moments up to the value of the rate function. Of course, what else should it be? Okay, so you can have exponential moments up to the value of the rate function. Of course, then you can try to go until the value, and then you can, but still, in general, this is what we can do without any kind of optimization. And this is, as you can see, this is the same formula we had before in the case of the exponential decay. So this was really, you just replace it and it's there. Okay, here we have, of course, the exponential decay of the overlap statistic being larger than k. All right, so, okay, having this, you have a lot of immediate applications. Okay, everything which is not running away will be just treated with this. The Borel-Cantelli theorem. Okay, you have exponential mean deviation frequency. You have the Temadi we saw. Then we have these Babnik-Chervonenkis, these inequalities of gamma type. If you have LDPs, then you have Kramer's theorem, Sarnoff's theorem. You can, okay, what we did is we look at Dembo-Zaitouni and we looked for Borel Cantelli, and this was the third example here. The method of moments in statistics. Of course, this is all the, for example, consistency of numerical schemes. You can just look how many times you will infringe with will trespass until to commit to the convergence almost surely. Right? So this is something which happens all the time. All right. So far, are you with me? Please. Now it's a good point to interrupt and to take questions. So just repeat very briefly what we did. We just showed a simple generalization of the first Borel Cantelli lemma, and then we applied it to the convergence in probability. So just going here. So this was the original question. If we have rates go to 0, what can we say about higher moments? And we can see that, if we have some kind of series being finite, then we have higher moments in this order of S. Independence improves things tremendously with typically exponential moments, and monotonicity gives us an exact formula, right? So this is what we just answered. And now we're going to try to apply this to a very special case, and these are the approximations of sample path properties of Brownian motion. Well, Brownian motion was studied, okay, I hope most of them are familiar with Brownian motion. Brownian was studied, of course, for all the 20th century with different kinds of approximations, and these are approximations in probability very often. And then you use the Borel Cantelli lemma in all kinds of things. Now we can quantify these things. So there are a lot of results which just can be quantified now. For example, you have the law of the iterated logarithm. You know that asymptotically, you will just comply with some kind of formula. The question is, how many times will you infringe until to comply with it? And these kind of questions. Right, so here we are. The basic idea, of course, in the past was just to hide all this probability in order to have a good and very nice description of the path properties. And now we're just coming back, we're just undoing this, and just taking once again into account the statistics in order to translate it into almost sure convergence with this kind of mean deviation frequency. Okay, this reverse engineering of these things. Okay, first of all, the most classical thing may be the construction of Brownian motion. You have the Wiener construction as it's written here. How is it done typically? You look at not only the sum, so this is a Fourier type of sum, and you look from 1 till j, but we don't look at j, so we look at packages of exponential orders of 2 to the j, and by the Pythagoras theorem you can just write down that this is just of order 2 to the minus j fourth. So then you use Markov's inequality for some kind of m here. Here we are, here are our moments, and then you can see that it's something summable, and this is how you get something almost surely. Then this means this is almost surely a Cauchy sequence, and it converges uniformly over 0, 1 in L2 and almost surely. Okay, the point is you don't know much more about this beyond that it's almost converging. If you want to do this almost surely, of course, the problem is that this guy here does not converge absolutely. So, okay, you cannot. If you do the same with the Cahun and Loew-Kosambi construction, you have the same problem. The good thing is that in L2 there are optimal rates which are known. So these are the optimal known rates, and of course you can estimate them like this. And this rate tells us that an almost sure convergence of order better than 2 to the minus j half is not possible. Okay. Nevertheless, the same problem, of course, does not converge. So this is why Levy's construction is much more important. For example, if you look at the book by Steele, here it's carried out all in detail. So what do? You have 0, 1s, IID, the zeta n's here. We have some weights, and then we have these kind of tooth function, which are just summed up in the right height by the lambda n's. Well, we have from there, you can show that it's converging almost surely. This is very nice, very nice pictures. And now we come to results which we have there. We can show that almost surely for any alpha, this is kind of error term, so being a little bit greater, for any alpha, and any j in n, there are random variables, lambda j of alpha, such that almost surely we can bound the infinity norm between Lj and W. Okay? So what we get here is an upper bound, which is in this case also known. Typically what you know is, well, there is some kind of random variable, which is something known, but typically you don't know the moments, and now we can calculate all the moments. And we have this kind of rate, which is the square root of j plus 1, 2 to the minus j half. This is something, well, the deterministic part is rather classical. What is not so classical are the moments of the random variable which you have here. This is not really related to the Borel Cantelli type. It's just a lot of calculations, 3 pages of calculating. And the good thing is that you can see here is we have some kind of Gaussian moments. This also has to do a lot with the independence, which just is underlying. Okay, and the point is that even those Gaussian moments, as you can see, it's e to the lambda j squared, here decays exponentially. So it's really, really strong convergence. So if we take an expectation to this guy here, then we have here, and with an expectation to this random variable, we get upper bounds, and these upper bounds are just given here in terms even numerically. Okay, so even we have good rates in a new topology. Is L2 of L infinity. Okay, so far it was not known to our knowledge. So then we want to have, for example, deterministic upper bounds, and we want to say something about this modulus of convergence. Well, we can quantify it rather well. So we have upper and lower bounds of the same type. These are exponentially approaching each other. So this is not the same, we don't know it precisely, but the error margin is going to 0. Then we can say something about the step-by-step error frequency. This means you simulate j, or j plus 1, you simulate j times, you construct j levels of the dyadic packages of the Brownian motion, of the powers of the Levy construction. And the question is, how many times do you expect errors of something greater than epsilon j? And this epsilon j is something which goes to 0 rather fast. This means how many times you would, the frequency of the errors which come up there. And you can say, and this is where our example 5, this with the Gaussian decay actually comes in. Here we get something which decays rather fast. So the number of the frequency of errors which are committed, the number of errors being greater than k decays very, very fast. Well, then we can do the same thing. Okay, I'll just skip this because it's less important. We can say something about, well, so we have always a play, right? So at one place you have very strong rates of convergence and you have barely summable. You have something which is barely summable, or you have almost no convergence to 0, even something constant, and you have a good summability. So there's a play between the almost sure rate and the number of errors how quickly you will just assume this rate. So if you have a very good almost sure rate, then you have to take a lot of time until you will comply with it. If you have a bad rate, then you might take it immediately. Right? So there's a play between good rates and the times and the number of frequency of errors which you have to take into account. Right? And so here we took the best possible rate of in the J, almost surely. And here we have something on the right which is barely summable, and here we get something which is which only gives us the rate of the Borel Cantelli lemma itself. So the first moment. This means first moment means that you have a decay of 1 over k, nothing more. Well, we can attack other classical results. For example, the Kolmogorov-Chentsov continuity theorem. All right, so typically, well, so the first part is just the classical theorem. So if you have this kind of, let's say, Hölder continuity, we have some alpha, beta, and c positive, such that the increment xt minus xs to the alpha is less or equal times c, and here we have the difference of the indices t minus s to the 1 plus alpha. So then for any gamma, which is between 0 and beta sobre alpha, and over alpha, sorry, we have gamma Hölder continuity. Right, so this is the classical result. And now we can say something about this the modulus of continuity of this quotient difference. So if you look at the Hölder quotient here, we have the difference here and st minus s to the alpha, and here we have the supremum over between, well, first of all, t minus s. Of course, it cannot be larger than this kind of t here. And then there's a random quantity. This means you have a random quantity and you can see how large it will be. So, okay, when this kind of Hölder quotient is satisfied, and of course you would like to have lower bounds of this. You want to know what is the minimal time in order to where you can count with this kind of estimate. And the point is we can actually give lower bounds exactly in the same idea as we had before with the overlap statistic. And the point for this is the h is a random variable which is approximated on the dyadics, okay, on smaller dyadics. And you can really write down some probability, and you can translate it into the exponential moments of something. Okay, and this is what we get here. We get lower bounds for this modulus of continuity of this Hölder quotient. All right. So if you ask yourself, how many times, if you have your grid here, and the question is how many times it will be bigger than 2 to the minus gamma n, being greater some k, so the number of n's, such that this is larger than this small error. And you can see that this probability goes to 0 here exponentially. This is an optimized quantity which just lives with the same with the same Borel Cantelli lemma. Okay, so the example is of course Brownian motion, where you have actually an equality here. Here we have the alphath moment of the standard normals, and here you can say that the moment of h, of the length of the Hölder exponent has a lower bound, which can be calculated explicitly. And if you do this for p equal to 1, we know that the expectation of this length is something which seems to be small. But if you take into account that this h has values on 2 to the minus n, you have to take the logarithm in order to understand what is the true size. So how many refinements do you need in order to comply with this? And this are just 7. All right, so this is not so bad. So what else? So we have Levy's modulus of continuity. So this is the classical result. So if you look at the ws minus wt, and you multiply it with a function in delta, which is the maximal difference between s and t, then you have this kind of moment. This is of course optimal. And you can ask yourself, is the lower and upper bound, do they behave similar, or are they very different? And here we get something that the upper bounds, if you have, for example, some kind of grid, exponential grid, some 2 to the n's or e to the n's here. So the question is, the problem is the probability that your maximum of those, so here you have the maximum of those divided by the respective quantity is smaller than something which is a little bit smaller than 1. How fast does it go to 0? So the number of errors of these kind of things being greater than k, so more than k errors of this type, and you can see that it tends to 0 very fast. It tends to 0 even at a Gumpel type. So this is double exponential. This is really, really good. Okay, for the lower bound, it's not so nice. It's still nice, but it's exponential, what you can see here. And of course, here you have to take into account more precisely the epsilons here. So you have an error fixed here, and you have the rho, and the rho is something which depends very much on the theta and the epsilon, so this is a tiny quantity. Nevertheless, it tends to 0 exponentially, okay, even if the exponent is rather small. You have the Paley-Wiener-Zygmunt theorem. Classically, it tells us that the omegas, such that the derivative, the right Dini derivative and the left Dini derivative being infinity or minus infinity, contains a event of probability 1. So, if you look at the approximation in the proof, how this is done, this is a dyadic repartition, and you ask yourself, if you look at the approximation of the difference quotient, how many times will you, if you allow this to grow even exponentially, with a power of 1 and 2 to the minus 2 to the 1 quarter. So this can be growing even. So you're asking, well, you know that the derivative will be infinity, right? So it can grow to infinity. The question is, how fast can it grow? And how many times will you trespass this kind of rate before going to infinity? And you can see that even if this grows exponentially, the number of times such that you have more than k of these errors decays, and you can say here this is exponentially. So this is even crazy. So you're approximating on a dyadic scale, and you ask yourself the derivative, if it grows exponentially, how many times will you see more than k errors? And you see it less than something to the minus k errors. So it's really going to zero very fast. So you have a very dichotomic behavior. Then the loss of monotonicity. Of course, we know that Brownian motion has no monotonic path, so in no subinterval you have any kind of monotonicity. And the question is, how fast do you lose this? And here you can just look at some kind of differences, and if you have something monotonic, you can say just it must grow all the time, or it must decrease all the time. And if it grows all the time, you can see the probability to have this decays at a certain rate. And the nice thing is, this is something, this is only 1/2 to the something. It's of course, being greater or smaller, it's symmetric. This means this result is completely general for all kinds of symmetric processes. This can be alpha stable, can be Cauchy if you want. So you can use it in many, many settings, not only for Brownian motion. So this is true, and the same rate is true for all of this. The right-hand side is, in fact, an optimized quantity over the Borel Cantelli lemma which we have. Please. Just this increment, exactly. Any kind of, well, here I just mentioned Levy process, but of course you can additive process, whatever. Yeah, sure. Thank you. Okay, then the convergence to the quadratic variation. Of course, there are classical results, and the results I present here maybe are not the optimal ones. But if you have some kind of grid, and the grid size tends to zero sufficiently fast, then you have the convergence to the quadratic variation almost surely. This is in the book, for example, by Schilling. So the new book about Brownian motion. It's very nicely written. We used it a lot. So now we would like to quantify this, and you can just look at the number of overlaps, just the numbers of errors you commit at a rate of at an error level epsilon. So if you have this kind of finite upper bound, then you can just estimate the probability. This is very general. And in the case, well, just going there, in the case of an equidistant partition, you can do even more. We can just calculate it directly. We have some kind of exponential decay. Exponential decay, you remember, this means exponential overlap statistic, and this is what we get here. So we get also some kind of exponential decay of this error of the convergence almost surely. So here, and the same is if you take some optimal rate, but I think that doesn't worth it. So the last thing I would like to mention are the laws of the iterated logarithm, because they are just so they're nice to see actually. Well, so the upper bound of the law of the iterated logarithm, sorry, this is of course not 1/2, this is 1 over t. So this is a t here. What we have is that for t to 0, of course by self-symmetry, this is also true for t to infinity. T to 0, you have this function, this lower function, which just gives you a very precise rate of convergence. I just wanted to see you. So if you have Brownian motion and you have this kind of function here, then we know that Brownian motion has to behave just like this in the beginning, and then of course it's going. And the question is, if you approximate from the right, how many times will you infringe until you comply with it? And the truth is, it converges rather slowly, not nice. So it really, really takes quite some time until you comply with this. Am I this doing? No. Somebody's just, okay. I'll ignore it for the moment. All right, so what we get here is, we take some kind of approximation of the supremum going to 0. And here we have all the constants in here, and for all thetas and all deltas, which we have here, we get some kind of k to the minus maximum of 1 and delta. So we need delta being greater than 1, for example 2, and here we get some kind of rate which is quadratic. Okay, so it depends, of course, how fast you go to 0 in order to quantify how many errors you will commit. Okay, you can do this also for Chung's other law. So I'm just talking about the supremum, how the supremum of Brownian motion behaves. The same thing. The rates are not very good here. So okay, this is something. It's nature. I cannot change it. And finally, we are looking at Strassen's functional law of the iterated logarithm. It's a quite nice thing. What we have is, you look at Brownian motion. We know that Brownian motion divided by this quantity here below satisfies the law of the iterated logarithm. All right. So this means if we just divide through it, we know it has to be finite. And the question is, if you run the time from 0 to 1, and we run through this process from 0 to 1 in all the times. So we go from 0 to 1 in the whole time space. What we get is that we have a family of limiting functions, and these functions can be characterized by some kind of energy, right? I can see this should be some kind of energy here. All right, so, and this is the classical result here. We have that this object here tends goes closely, or tends in the Hausdorff distance to k to the 1/2. So what we can do is, if we have some kind of larger energy, this means we allow some larger quantity than just 1/2 here, a little bit more. What we get is that we have the distance between our renormalized function even growing with the rate q to the n, q being greater than 1, this means tends to infinity. So the number of errors committed of being greater than epsilon, being at a distance to this kind of set at a margin larger than epsilon, and this number being greater than k, decays like k to the -1. So this is just summability, nothing more. It's just a distance which happens here. If we have some kind of large energy, we allow for something which is of a set k 1/2 plus eta, and eta is large, then we can just give, once again, some kind of rates which are better in orders of p, and this p depend on just this kind of etas here, right? So what we get is, if we allow a larger set where we go, then we come there quicker, and the number of errors before complying with it decays faster. All right, I think this is it, and here are the two articles where all this appears. And the first one is the article with Luisa. So this was the elementary part, and the second part was the not so elementary part, I guess, about Brownian motion and its approximation, and it's on archive. Thank you very much.
Thank you, Michael. It's time for the questions. Any more questions? Later on. One quick question. So you mentioned in the beginning, after the fundamental results, some applications to strong numerical approximation for SDs. So do you have any improvement?
So what we have so far is so what we have so far in the article with Luisa is this is in statistics and probability letter, so you know there's a page constraint. So we're looking at an application which is maybe the dumbest thing you can think of. You just make more and more subdivisions, and the question is how many, and you have a scheme which converges almost surely. Strong convergence of, for example, SDEs. Okay, this very complicated thing in the Klöden-Platten book. And if you have a rate of convergence which is greater than 2, then we can actually give an improvement. We can say that the number of errors, so if you make this kind of refinements, and you make many refinements, the number of errors, number of times when you commit some kind of error of size epsilon has to decline like something, and this something is if you have a rate, a scheme of order greater than 2, then you have 2 to the minus 1 plus k plus, and this difference greater than 2. So we can, at least this is some kind of sanity check. It's not worked out so far, the day has 24 hours and things like this. So, but we're trying to apply this, of course. So it's quite natural to apply this for numerical schemes. Yes. Yeah, it should be applied. Yeah. I guess it should be. Yes. Exactly. And this should, this should be.
Do you know what is the rate we can get from this technique?
Not.
Should be exponential again.
Yeah, exactly. Okay, I don't remember it now, but yes.
Yes, it's not far.
Yeah, but you can use it. Yeah. Okay. So of course there are many natural applications. Whenever you have some kind of convergence in probability which is sufficiently fast, you can just use the excess of this convergence in order to convert it into some kind of almost sure statistical quantity.
So thank you very much again, Michael, for the very nice talk. Thank you. It's time for the lunch. Oh, no. The probability session, we have a session, a small session now on the math department. Then we have a lunch here.
Was it understandable? ¿Se puede entender? ¿Estuvo claro más o menos? Sí. No, es